if they're all their algorithms are local, you know.
In fact, sometimes I show up as a tutor on a Wisant because I am a tutor for Wisant. But
yeah, I see Wisant here.
People can't find me that way. They can only find me through my Wisant account. And that doesn't give my name or phone number or website. So that's not terribly useful for me.
That's not good.
So, all right, let's see. It's a good thing I have you. I don't have any calculus students this season yet.
Oh, really?
It's kind of odd.
Huh.
Yeah, my one, Emily, she finished up Calc BC. She's still in high school, but she's doing calculus beyond me now.
Oh.
We got to know.
Do they teach in high school like
They do.
stuff that's beyond that? Or?
They do. It's amazing. And in fact,
Wow.
the title of the course is Beyond Calculus. And I said to her, well, how is that? I mean, how can everything's calculus? Beyond calculus, everything is still calculus. At least that's what I thought. But maybe I'm wrong.
Like linear algebra?
Well, but even linear algebra. Well, linear algebra, I think, gets more into matrices and stuff.
Yeah.
And maybe that's not calculus. But my impression was, I mean, if you look at all the higher math equations that Einstein figured out the theory of relativity in it, it's littered with calculus expressions. So
yeah.
I can't see calculus ever going completely beyond it.
Yeah, maybe it's all just related in one way or another after
I
that.
think it is, yeah. You know, and in fact, that makes sense, especially when you read that calculus is the most important discovery that humans have ever made in math, and perhaps at all. And so you know it's got to be awfully fundamental to all higher maths.
Huh.
Let's see, I think we did 12. My notes say that we did 12. Yeah, I remember how we did 12. We used L'Hopital's rule.
Oh, right.
And it took one iteration before we got an answer. Okay, and then 13 was the question that we need to come back to. In other words, that 13 is we need to take the derivative of parametric equations. All right, let's look at 14. God, I'm really frightened that I'm going to forget the calculus that I know. I mean, I have
it must be really a minority of high school students that are doing calculus or even beyond.
I would say that in a given year, I might have 10 calculus students out of 60 for the year.
Oh, okay.
If that, yeah, that's probably a proper ratio. So it's pretty unusual now that I don't have any. And I am finding that, boy, it's real easy to go a year without covering something. Like I got this pre-calc student who's an IB student, and they cover stuff that most of the pre-calc students don't cover. Right now she's covering binomial expansion. That's good stuff. I haven't done that. I probably haven't had a student do that in 2 years. And, boy, I don't remember that stuff. At my age, you go that long without doing something. So part of the secret of staying on top of this math is to do lots of it and broadly.
Yeah, I guess so.
That's why I'm worried about the calculus. I think if I went a full year without doing it, I would forget an awful lot of what I have learned.
Huh.
So let's see. Compute this integral, number 14. What do all these answers suggest?
Well, I'm thinking there's got to be like a 1 over something that turns into a natural log.
Exactly.
Because I see the absolute value, right?
And what it probably suggests is, remember when we did all of these problems by partial fractions?
Oh man, yeah, I remember that we did, so I don't remember how it all.
You got to have it worse than me because it's been so long since we've done so much of this new stuff that you learned. In fact, I hope I can remember how to do the partial fractions. The first clue that it's a partial fractions is we have a denominator that is fully factored, but even if it wasn't, it would be a quadratic. And you generally know that quadratics need to be factored. So let's see, the integral of x plus 3 over x plus 1 times x is the integral, hold on a moment, let's see, that's going to be the integral of a over x plus 1 plus b over x. In other words, if I was adding a over x plus 1 plus b over x, in fact, let's write it like that. Here, let me do it like this. X plus 3 over x plus 1 times x has to be equal to two fractions added together. A over x plus 1 and b over x. In other words, if we were going to do that, we would multiply the bottoms to come up with a common denominator, and then we would add the tops. So when I write it like this, I can now say that x plus 3 equals a plus b.
Oh, wait, now I got confused.
Yeah, that's because I didn't do it right. It's equal to ax plus b times x plus 1. Is that better?
Oh, okay, let me see here. Okay, we had a over x plus 1 plus b over x. Now that a over x plus 1 and b over x, that a could be like...
It's some number. It's going to, well, could it be? I think it has to be a number. We'll proceed from this. Just, in other words, you can see that when we add it together comes out to be a over x plus b times x plus over 1 all over the common denominator. Right? In other words, just using algebra. When I add that together, I get this. Which means,
yeah, okay, I think you're right.
Which means now I can write this. Here, let me blow it up a little bit. Go scroll down. In other words, I can write x plus 3 over these two factors is equal to a times x plus that over those two.
Mm-hmm. Yeah.
Okay, so now I can equate the numerators.
At the first step,
where
it was like x plus 3 over that, and then a over x plus 1 plus b over x. That's not making any kind of intuitive sense to me.
It's separating, in other words, you're separating the partial fractions. Let's look at it from the other direction. If you started with a over x plus 1 plus b over x, how would you add those together?
Well, you'd have to get the common denominator, say multiply those two denominators.
Which is this.
And then you'd have, so then you'd have a times x plus b times x plus 1. That equals x plus 3?
Yeah. In other words, this goes into this.
Okay.
And since we're on the left side, we're looking at that denominator. Therefore, this x plus 3 must equal my ax plus bx plus 1.
Okay, I guess, yeah, it works out in the proof. I still intuitively, when I go through it,
let's go through it, and once we get the answer, we can go backwards, and you'll see it, I think. Okay?
Yeah, it made sense when you did it just now. It just like...
Okay. Now, the next step is trying to solve for a and b.
Okay.
Well, I can make b go to 0 if I let x equal minus 1.
Okay.
So I'm going to plug in minus 1 for x, because this has to be true for all x. So I can pick any x I want, and this has to be true. Well, if I click minus 1 for x, I get this, plus 0.
Then, okay, okay, so we get negative 1 plus 3 plus negative 1 plus 0, right, okay.
Okay, so now that solves a equals negative 2.
Okay.
Okay, so I can now go up here and write in what a is. Now, how can I solve for b? Well, I can let x equal 0.
So you
That will
solve
make a disappear.
in the original equation?
Well, this equation is what's governing everything at the moment. Trying to solve for a and b.
Okay.
Okay? So, actually, I don't even need to pick a number for x. I solved for a, so I could plug in a as minus 2 and simply solve this equation. But this technique is useful. It's easier. In other words, since this has to be true for all x, then it's got to be true for x equals 0. And if I let x equal 0, then I have 3.
I thought we were letting x is negative 2.
Well, we started out, no, we solved for a, and it solved to be negative 2.
Okay, okay.
Oh, my computer's going wacky again. Where'd that come from? Yeah. Hold on a second. Let me move stuff out of the way. May have to reboot and call you back. If you lose me all of a sudden, that's what's happened.
Okay.
And this thing never gets better. But so the first time we substituted minus 1 for x. That allowed us to solve for a.
Okay.
Well, if we go back to exactly the same equation before we solved for a, let's let x equal 0. Let's let x equal 0. And that's going to let us solve for b. Okay? When I plug 0 in for x, I get 0 there, and then I get b times 1. So b equals 3.
Yeah, one moment here. So before we solve for a, but we solve for b instead by letting x 0. So,
Right,
okay.
and that gets rid of the a term, and that's what allows us to solve for b.
So we have 0, oops, we have x plus 3, no, we have 0 plus 3, okay, is equal to a times 0 plus b times 2. Okay, and that leads to...
All right, so I can go up here and erase the b and put a 3 in there. Now, let's just make sure that that works. Okay, is that a true equation? In other words, this is what we're trying to integrate, and I'm telling you that it's equal to minus 2 over x plus 1 plus 3 over x. Well, let's check. Let's see what we get when we find a common denominator. And okay, so this is minus 2x here, plus 3 times x plus 1. That's x plus 3 over x plus 1 times x.
All right, so we went back, we subbed in negative 2 for a and 3 for b.
Uh-huh.
And then what do we do after that just now?
Well, just verifying that that's true. In other words, if you add minus 2 over x plus 1 to 3 over x, you get this.
Oh, I see. Okay.
Okay?
Okay.
So as all
just,
partial fractions is undoing that.
okay.
Yeah, I'm not doing that to my screen either. Let me reboot and call you back in 5 minutes.
Okay, sure.
All right. Well, rebooting isn't even easy. I don't have any control over my mouse.